you added, you modify one original equation and add two constants in the simplification equation. So that is committed relaxed RSAS. And yeah, so the protocols of NOVA is the protocol of NOVA is to reduce two the committed relaxed RSAS into one committed relaxed RSAS. Yeah, that's the for the NOVA's folding scheme. This is the R1, R2, and R1 prime are all of the committed relaxed RSAS, and the protocol is goes like follows. Yeah, so let's expand everything, and you can see all the items in the instance and the witness are updated or to update. So first, the prover computes cross terms, and T is computed from from Z1 and Z2 and EC, and U1 and U2. And then the prover need to commit to T and send the commitment of the cross terms to verifier, and then the verifier challenges. So for a non-interactive folding scheme, the verifier can use a hash function to the transcript to generate the challenge alpha, and then verifier and prover can both compute can both update everything in the public instance in the public part, that's the instant part, including X, U, W, and the commit and the W and the commit E. And P itself can compute the updated witness. So that is the case that the R1 and R2 are both committed relaxed RSAS. And let's let's see if R2 is a regular RSAS, what will happen. And in this case, for a regular RSAS, the U is 1 and E is 0. So this is the trivial. This is a special instance of RSAS, and then everything, including E2 and U2, can be removed from the computation. And yeah, so for example, for U, you only need to add alpha, the challenge to U1. So U2 is already 1, so you don't need to consider. And for E's commitment, you only need to add the alpha the T commitments to E instead of having a E2 commitment. Any questions in this NOVA's recap? Okay. So during the whole process of folding scheme, the verifier's part should be expressed in the arithmetic circuit. So the cost of the verifier, folding scheme to verifier, is very important, because it should be expressed in the circuit, and if in the final start or the decider's part, the circuit size matters. So let's see the dominant part for the folding scheme verifier, and then we can find that there are two group scalar multiplication inside the verifier in NOVA. So so the main cost of the verifier circuit is the two group scalar multiplication, and so this is the opportunity to optimize. And OVA and MOVA are NOVA and OVA and MOVA focus on this optimization opportunity. So what OVA does is like one observation is that it can combine the U and the E into one commitment. So it just removes U and E and builds a new commitment Q. And Q is and the relation and the Q is defined as the commitment of W and commitment of E. That's a very natural replacement. So in the satisfaction part, you don't need to check W and E separately. You need to check one commitment here. And you can notice that there's no E inside the limited part. That's because E can be computed from Z, right? So E without loss of generality, E can be removed from. E can be non-deterministic units. So the basic idea of OVA's relation is to remove W and E's commitment and make it in Q. And maybe it can be removed here. And the protocols of OVA's folding is like this. So it folds OVA's relation and regular RSS into another OVA, a new OVA relation. And what is updated is the XQ, it's the XU and the Q commitment and the W. So it works a lot, very similar to NOVA folding scheme. So prover first computes cross terms T, just exactly same as NOVA, and then prover commits to this commits to W2 and T, and they connect those two commitments together and send to me. So P still need to commit to this the cross terms and the second instance witness, and we then generate the challenge, and V and P both compute the updated XU and Q commitment. So the Q commitment updating is very similar to it's very similar to E. To W, or to E. It's just the old one plus the alpha multiplied the threshold, and then P just the prover can update the witness just like NOVA does. So what the benefit of this protocol is? Inside the verifier circuit, only one group scalar multiplication is added. So two becomes one, and one explanation is exponent operation is saved. Yeah, that is OVA, very simple. So what is added? What it added is in the checking process, the decider need to check, still need to check W and E's commitment and against the Q. So this is OVA. It's a slight improvement of and and so my final scheme is MOVA. So MOVA is a little bit complex and so the effect of MOVA also reduce one group group scalar multiplication inside the verification circuit. And it also does some modification to the relaxed RSS. So in MOVA, we still need W's relation, W's commitment, and we don't need E. E's commitment is saved. So therefore, I recovered it, and now this is CR RSS, right? And now we remove so MOVA removes E's commitment and replace it with U. With V and R. Yeah. So E is removed here, and since there's no E's commitment, we don't need to check E, and but we need to check V is E vector, is slack vector is ML is evaluated at point R. So R is a multi-dimensional field element double. So this is ML. This is ML. It's a multivariate polynomial. And yeah, so the basic idea of MOVA is the iteration is that the E is already decided by can be decided by X and W. So we don't need to commit to E. Instead, we need to we only add the evaluation of E's MLE at the point R, and the value is V. So the protocol runs like this. I borrowed the index from MOVA's paper. So at the beginning, we have two instances. One is MOVA's accumulated instance, that's R1, and another is MOVA's fresh instance, R2, which is a regular RSS. And using MOVA's protocol 3, we can transform the RSS into a trivial case of MOVA accumulated instance. That's R2 prime, and then you can use so R2 prime and R2 and so R2 prime and R1 are both MOVA's accumulated instance, but they have different R. So they have different evaluation evaluation points, and then using MOVA's protocol 4, you can unify the R. So after protocol 4, you can have a pair you can reduce the pair of R1 prime and R1 into a pair of MOVA's accumulated instance with same R. So R1 and R2 becomes a unified R. And but R3 is still not one relation. It's a pair of two instances, a pair of two relations. So so the MOVA invented its own MOVA's volume. That's called protocol 2. And protocol 2 is to reduce two MOVA's accumulated instance with same R into one instance. Oh, yeah. And that is the final output of MOVA. And this instance can further be passed as the accumulated instance. So, yeah, any problem here? Yeah, so this is the process. Yeah.
So, any details, more details about R3, the relation?
Yeah, R3 is it looks like that is R3 attests the existence of R. The R satisfies both relations. But
so the two R ACC kind of we should have the same, the small
same,
R, right?
Yeah, same small R.
Okay.
Yes,
okay.
yes.
But here, the R1, R2, small R1, small R2, so in protocol 4, so kind of
yeah, unifying the
Okay.
R1 and R2 into
One.
a new one, unified one.
so R is kind of a randomness, right?
Yeah, right. Yeah, like a So the basic protocol 3 is the simplest one. It makes a regular RMSS into MOVA's instance. So it just adds U and W's commitment and V and EW to in the instance. And the commitment of W is just the commitment of W. It's trivial. And the R is generated by V randomly. For example, you can have X and the W commitments hashed. And U is what? So just like the commitment relaxed RMSS in NOVA, U is 1, and E of course is 0. And so E is a 0 vector. So the MLE of 0 vector evaluated at random point is also 0. So V is 0. So the result is U is 1 and V is 0, and R is randomly selected sample. So this is the And protocol 4 is more interesting. So it unifies R1 and R2 into a single R. It uses it borrows the point versus line argument trick, which can be found in there's book. And so the interface. The interface is this, and what is updated is only V1 prime and only each other's V and R. So everything else is not changed. Okay, so the symbol case is R1 equal to R2. So then you just let R be R1 and R2, and V is changed. So let's look at the non-trivial case. Which is R1 is not R2. This by using the point versus line trick. First, we have a line passing R1 and R2. That's the line is linear map. So the linear map F. So F0 is R1F and F1 is R2. One of the construction of this unique line is 1 minus XR1 and XR2. That's the line passing R1 and R2. So it's R1 and this is R2 iteration. And we draw a line, and the line is F. And R1 and R2 are both field element. It's just they are both high dimensional field element tuple. And then P computes two polynomials and send to V. The two polynomials are both univariate polynomial. They are called H1 and H2. So H1 is E1's MLE combined with F. So X is univariate, and H1 is also a univariate polynomial. And so if X is 0, H1 0 is V1. That's included in the instance. So this is statement 1, and statement 2 is also the same. So the verifier needs to check both statement 1 and statement 2 are correct or not in the non-interactive folded scheme verification circuit. And then verifier challenge generate a challenge randomly beta, and you can see this is X is 0 and this is X is 1, and then it generates a random point beta. So this is X equal to beta, and this is the point F beta. So F beta will become the new random point R, and the new value evaluation of the instance will be H1 F beta and H2 F beta. So this is the this is what MOVA's protocol 3 and probably and here. So the trick is you draw a line and select a random point, and then both instances will be updated, and the evaluation is should be checked on this on this point. Sorry, there's a probe for it. And in the Protocol 2, this is the Protocol 2 is the MOVA's folding. So it folds two instances of accumulated MOVA instance with same R into another folded instance with R unchanged. And what is updated is and the process looks very similar to Nova. So the process it starts from P computes T, same as Nova, and then P computes the MLE of T evaluated at R and sent to V. So this is what MOVA the difference between Nova and MOVA. So P do not need to commitment to prover that does not need to commitment to commit to T and send to V. So prover just computes the MLE evaluation, and then verifier challenge with alpha, same as Nova, and prover and verifier updates XW commitment and U. These are same as Nova. And then the what is different is that the V is updated. So instead of update E commitment, they update V. So the update of V is very similar to Nova, but with different variables. And then prover updates witness W or and even E, just like same as Nova. Yeah. And this is the MOBA's folding. So in this folding, you can see there's only one group exponent operation. So in the MS, in the non-interactive folding scheme verifier of MOBA, there's less cost. And also, the prover does not need to commit to T, which is it could be M elements. So both verifier and the prover of the folding scheme can be saved. So that's MOBA. No, I will not. Yeah. So just wrap up our talk. Nova is a folding scheme which the verifier which need two group scalable verification. Nova and MOBA aim to reduce the cost of verification inside the folding scheme. There's also more XOVA's scheme like LOA and that expose the folding. Yeah, that's my presentation.
Is it possible for you to share these notes?
Sure.
So what are new features about the Nova?
LOA, it's a lattice.
Okay.
But no published full text yet, so it's will be released in next time. Asia. Yeah, I will share this slide later. So if you mention and have a person.